Three, two, one.
Hello everybody and welcome to Tonight in STEM. This is the show where I interview professionals in the field of, well, science, technology, engineering, and mathematics. Today I have a graduate student, a PhD student, who I would like to introduce to you guys. His name is Juan Lopez. So let's go head over and say hi. How are you doing, Juan?
Very good. And yourself?
I'm good. Thank you for asking. How's the weather in Michigan?
It's quite nice for Michigan. We're in the high 60s.
What is quite nice for Michigan?
High 60s. High 60s.
Okay.
Yeah.
That's good. It's better than negative numbers, right?
Exactly.
Well, thank you for being on.
Mm-hmm. Thank you for having me.
Yeah. So before we get started, I guess I should introduce Juan Lopez. Like I said, he is a PhD student in the philosophy of material science and engineering at University of Michigan. He's written a few papers. So one of the titles is Self-Assembled Nanoparticle Anti-Glare Coatings in the Optics Letter magazine. That was in 2012. He has one right now, Coexistence of High TC Ferromagnetism and N-type electrical conductivity in some compound that I'm pretty sure I'll explain later, right?
Yeah.
That's the Journal of Journal of American Chemical Society.
Mm-hmm.
And then he's preparing one, might be out soon. Synthesis crystal structure, a magnetic ordering in this compound that I can't talk about. Well, I can talk about it, I can't pronounce it. He has several honors: National Science Foundation Research Fellow, Rackham Merit Fellow, UF Ronald E. Mcnair Scholar, Ford Foundation Fellow, Honorable Mention, and Outstanding Student in Chemical Engineering Scholarship. He's currently a graduate research assistant working on synthesizing in a high Curie temperature N-type ferromagnet semiconductor and evaluating the mechanism for spin polarization and carrier mediation. I believe so, yes. So I'll let the expert talk a little bit about this a little later on, but we'll get started. And Juan Lopez, how did you get started in science, in technology, engineering, and mathematics, and what's known as STEM?
I would have to give the credit to my high school teachers, actually.
Okay, awesome.
So when I started high school in 9th grade, I was first thinking that I would like psychology because I read The Chosen by Chaim Poltak.
Okay.
It was on our required reading list, and I really enjoyed it. And I was like, "Whoa, psychology is really cool! I could see myself doing this kind of thing." And then I had a very good geometry teacher, Mr. Sachs, and he just really inspired me. He helped me out a lot, and yeah, that kind of started
university
it.
Level.
This is high school level.
High school level.
Yeah,
And
then
sorry.
That's when my ideas of what I could do really started to change. And then I first started in mathematics, and then kind of went into science, and essentially, went to college and majored in chemical engineering.
Chemical engineering, yes. So let's step back a little bit in how you made that choice to go to the university. Was that kind of implanted? Did your parents kind of tell you should go to university? How did that happen? How did the idea develop?
The idea first developed in my chemistry class in high school.
Okay.
Under a very good teacher of mine, Miss Alonso. She really helped me and coached me to kind of to really understand the world, the chemical world, the small world, and it was beautiful. And then
that's a nice way to put it.
Yeah, well, it's essentially a beautiful world. We just don't see it enough, but if you could see it, it's wonderful. And I wanted to see more of it. I wanted to understand a little more of it. And she told me that there are options. There's always college, and then you can major in it, and then later on go work in that field. And I thought, yeah, well, that's really cool. I could see myself doing that as well.
Oh, wow.
Mm-hmm.
Did anything specific at that time pop up in the chemical field that you really were interested in?
In high school or
yes,
in
high
college?
School.
More than anything, just the kinetic theory of gases fascinated me. Just being able to understand how the density of gas molecules in a container can affect the pressure, and how their and basically how their density can be affected by the size of the container they're
Correct.
in or the temperature at which they're at.
Correct.
Yeah.
Okay, I don't want to butcher this, but this is the classic PV-nRT formula, right?
Yep, that's it.
All right,
That's
good.
it.
So I still remember things.
Yeah.
Yeah, okay, that's awesome.
Mhm.
And then you went to the University of Florida, correct?
Correct. Mhm.
And then how did you end at the University of Florida, and why chemical engineering?
So chemical engineering because I really liked chemistry and I really liked math and I liked physics and I kind of wanted to combine everything. And I was reading a pamphlet, New York University NYU pamphlet on a bunch of majors they offered.
Okay.
And I was like, I guess what could I do? And I was looking at it, and then chemical engineering said a merging of chemistry, physics, and mathematics. I'm like,
Oh, wow.
I think that's it. Yeah.
Yep, that's it. Yeah, because actually one of the questions I was going to ask you is, okay, you're interested in chemistry, right?
Yeah.
Naturally, logically, it would be, okay, I want to be a chemistry major. But like, what made you tack on engineering to that? But I guess you answered it, right? It's the mixture of all these together.
Exactly.
Can you elaborate a little bit more on that?
More so, it's not only understanding how these molecules and compounds come to be, but also what makes them possible. So then chemistry kind of details like the kinetics and the stability of the compounds, and then physics kind of goes more into the atomic molecular forces that go into making them stable. So like really, there's no clear line, but at the level at which you want to understand the material and how they work, it's a bit of both. You need to understand how they're made and what makes them stable and how that stability is an effect of a variety of other factors. So essentially, for what I wanted to do, understanding materials and designing materials and compounds, you kind of need a little bit of both.
Correct.
Yeah.
Wow. Okay, that is fascinating. Just integrating all these subject matters together. So you're at the university. You get your chemical engineering degree.
Yeah.
Was that the end, or who pushed you over into getting a PhD? Who inspired you, or how did that develop?
Again, Miss Alonso.
So we have a key person in your life,
Yeah,
right?
yeah, she really affected my life trajectory a lot. So then again, I got to talking, like, if I want to pursue this, like, what can I do? And she said, well, there's always college. And then she had a hunch, because she could tell I was very curious. And she was like, and then if you want to go a little further, you can always go to grad school and pursue a master's or even a PhD. So that kind of implanted the seed. And then once I was at college, I kind of began to realize the different levels, bachelor's, master's, PhD, what they all mean, and what you need to do to attain each one. And the level of study changes. Right.
So why not a master's? Why a PhD?
So a master's is beautiful because, like, there's this diagram online, and I like to use it to kind of explain. Okay. So if you kind of take all of human knowledge, everything that's ever been discovered and made and invented, and put it into one large circle, right? If you get a bachelor's in something, right, you're basically just like a little blip in the center. You're just starting to get to know how everything started and basically the fundamental laws of that field, right? And it doesn't go all the way around. It's just literally a little blip because you're specializing in this one particular field, whether it's mechanical engineering, physics, chemistry, art. You're learning all of the art, or basically the beginnings of the art world. And then the beautiful thing is that with a master's, you take that little blip and then you extend it further to.
So I did a quick search.
Yep.
While you were talking, is this what you're talking about?
Exactly.
Okay.
That's what I'm talking about. Yeah. So then, and then you basically go to the outside of the circle completely. And then a PhD is essentially, okay, you've mastered all of the material in that field, and now you want to add something new, add something more. Increase the radius of that circle. Just push that limit just a little more, expanding the boundary of human knowledge. And that's basically what I found amazing, is like making an impact in some way, helping the world in some way. Yeah.
So you're a very curious person, seems like.
A little bit,
very fascinating. So, how did you come up with this diagram, or where did you find it?
I found it first as a Mcnair scholar at the University of Florida.
Okay.
The Mcnair Scholar Program is basically like, I would say, a grad school boot camp. It's
Okay.
basically for those who have the desire to go to grad school. They apply to this program, and if they're accepted, then they're given a significant number of resources to basically help them achieve their goal of going to grad school. And they have a bunch of seminars and workshops on what it even means to get a PhD, and that's basically where I first came across it.
Okay.
And
I bet
that's
you
when
were sucked into that, right?
I was.
Exactly. So, what made? How did you make the choice to go to the University of Michigan?
So of all of the grad schools that I got into, the University of Michigan, one, had the best environment.
Okay.
What I mean by that is the academic environments, naturally because of the nature of the environment, it can be somewhat competitive. And I didn't want to go into a department at a university where I would be competing against my peers. If anything, I wanted to help them with their projects, them help me with my projects. And University of Michigan had the environment which seemed to foster the greatest number of connections between people within the department, outside the department, and across universities. And it was just the most welcoming in the end. I felt wanted here at the University of Michigan.
How many other universities do you apply to?
I applied to...
And I guess tour of, right?
I applied to 8, I believe. I can't remember now.
It's been a long time.
And I believe I got into 5, and I toured only 3 because it only worked out for my schedule. No, sorry, I did tour all 5, but then when it came down to making the decision, I was down to 3. But then in the end, I had done a summer research program here at the University of Michigan, and I fell in love with the town and the research. And yeah, I kind of...
The rest is history.
Yeah, much.
So one of the topics that I want to cover, and the reason you're on, is to talk about how to find the right advisor.
Okay.
And I want to kind of touch on that because when you apply to a program, PhD program or even a master's program, when does the advisor come into play? After you get accepted, and how do you choose that advisor?
So the connection with an advisor should start a little before you get accepted. If anything, right when you start applying. And the nature of the relationship, this relationship that you're going to foster, it's very different for very many people. So for example, I did a summer research program here at the University of Michigan as an undergrad. I was in my junior summer at UF, and I applied for a summer research program here, the Summer Research Opportunity Program. I got accepted to do research under Dr. Peter Green, who does a lot of organic photovoltaic cells and polymer physics and polymer dynamics research. So then that was something that I first got introduced here. That's how I first got introduced here, and I made my connections here at the University of Michigan through that program. However, if you're interested in an advisor and a particular field of research, you should usually email that advisor a little beforehand and start, an email thread, getting to know him, asking him questions, how he likes to run the lab, where he sees his research going, how is he going to accept students, that sort of thing. So it should start, if not at the time of application, when you're preparing your application materials, or a little before even, getting to know a professor and then maybe dropping their name in your application.
Correct.
Yeah.
So it seems like even before that, maybe you should look into, maybe you don't want to know which university you want to go to, but it seems like you should probably do undergraduate research opportunities where you can meet these advisors.
Exactly.
The idea of kind of what you did, right?
Yeah.
And get to know the advisor, what the research is. If not, how do you find these advisors?
So one of the ways is just asking. Is at your local university.
Okay.
If you're in college, if any professors are doing research, just ask them. Email them, say you'd like to meet with them, and maybe talk about a possibility of working for them. Some of them will be open to the idea. Some of them will say no because they literally just don't have space, and they have just a ton of students to manage already. And you will get a no. When I was looking to do research as an undergrad at UF, I got 3 no's before my advisor, who I published under at UF, finally said yes.
Okay, and
So yeah, so first asking and emailing a professor, that's a good way to kind of get started. Even if it's research that you're not that much interested in,
yes.
just get your foot in the door, start getting some research experience, and then that'll make you even more marketable in the future when you do find someone that you really connect with and that you like their research.
Okay. So I'm assuming, is there a directory of advisors, like where? Do I just search? Let's say I want to go to a specific university. Do I look at their graduate programs and see the advisors available, or how does that kind of happen? Let's say you haven't done any undergraduate research. You don't have any of that experience.
hmm So a great way is to ask other professors. So a lot of it is essentially limited to the type of research, to the
Okay.
field of research. So say that I'm researching magnetic semiconductors. So then if I wanted to find other professors who are doing magnetic semiconductor research, I'll basically look them up in Google. Just type in magnetic semiconductor, like university or something,
Mm-hmm.
and then a number of professor profiles are going to come up. Another great way is usually there's going to be one or two professors at your university doing that research and sitting down and
Okay.
talking with them, asking them who are people in their research field who are doing the kind of research that you want to do. And of
Okay.
course, asking that professor to do research under him as well at
Yeah.
the university.
You don't
Yeah.
have to leave them out.
No. So, yeah, starts with Google. Google's your friend.
Google's your friend.
Yep.
So what are let's say I have 5 advisors that I like, that are kind of doing research in fields that I'm interested in. What things should I look for the right advisor? Am I concerned about funding? Am I concerned about their space? What things should I really look for? And what questions should I ask also?
I would say more than anything is three things. The dynamic with your advisor, your relationship, the dynamic with your group, because you're going to be seeing these people every day, you're going to be
Okay.
working alongside them, you want to make sure that you work well together. And three, of course, is funding.
Funding.
You don't want to be paying for a PhD out of pocket, because it is pretty pricey. It is fairly pricey. Yeah. Sorry. I'm getting tongue-tied.
So you mentioned funding, that magic word. We all care about
Yeah.
money.
Mhm.
Are some advisors just looking for individuals who have, I believe, scholarships or fellowships?
Yeah. If you have a fellowship or a scholarship, you are more likely to be picked up, because the way it works as a grad student is you are either funded by your professor or you are either funded by another source,
Okay.
external or internal. Like you're on an internal fellowship, for example, the Mcnair Fellowship is a fellowship that the University of Michigan offers me, and that pays for me. And then there are other external fellowships, say like the National Science Foundation or the Department of Defense fellowship. There's also the SMART fellowship. So if you get external fellowships, you are more likely to be picked up by an advisor, because then he won't have to pay for you, right?
Okay.
Because
That
either
makes
your advisor
sense.
pays for you or someone else does. And if someone else is paying for you and you want to work for that person, they're more likely to take you on because you're completely free for them.
So, and then at what point do you apply for these fellowship scholarships, and how do you get them?
So one of the ways to start building up your application for these fellowships is to have research experience. Again, research experience. So look at your university. Start doing research as soon as you can, if you'd like, or if you're interested. Also, if you're not that interested, it's just something else that you could put on a CV that could make you more competitive if you do end up wanting to go into industry. But yeah, research experience.
Okay.
Start doing research as early as you can, even if it's not in something that you're completely interested in. Say I wanted to do like metals research. Like metals are cool, but it's just not what I'm passionate about.
Correct.
But if I had to, then, if I wanted to, I would do metals research just to get my foot in the door, get a little bit of experience, and then go on from there.
Let's say you find an advisor.
hmm
Are you stuck with him for the rest of your graduate?
So yeah, this is a bit of a touchy subject within the grad school community. And the thing is, if you're not having a very good relationship with your advisor, and you feel like you have to leave, then that is a very personal decision.
Okay.
I have known people who have switched groups and it ended up being better for them. Just make sure that you don't burn bridges with the other advisor. But usually, once you pick an advisor, you're with him until you graduate with your PhD.
So it is very important to find that right advisor for you for this. Okay.
Definitely. You're gonna nowadays. I think nowadays the average PhD is about 5 years, which is a little longer than the average marriage, I think. So.
Wow, nice little fact. I like that.
Yeah, you have to work well.
So how long is a PhD usually last? So you said 5 years, but I've heard 7.
It depends on the nature of your work.
Okay.
So if you do experimental work, naturally you go a little faster because you're doing things and then you wait for it and then you get results.
Okay.
So it's a little faster time window. So usually experimental people get done anywhere between 4 to 6 years. Okay. 5 is the average. If you do theoretical work, if you're just completely doing mathematics and trying to figure out basically the math of a particular system.
Correct.
So, for example, someone can do molecular dynamic simulations, and that's looking at doing calculations and studying the interactions of multiple bodies as simulated by these mathematical equations. And then that, because of the nature of the work, right, you're coding a lot, you have a lot of bugs or a bunch of things could come up. So naturally, theoretical work can take a little longer.
Okay.
So
I'm very familiar with bugs and coding, yes. Awesome. So another subject I want to kind of dive into is the balance between your current work, your graduate work, and life. Mm-hmm. I know as engineers, sometimes we don't have a life.
No.
But imagine we still need to talk to our family. Maybe some of us might have jobs or anything. How do you manage your time? How do you organize your schedule, your research, and other outside activities you might have?
So first of all, I try and create an action plan. What needs to get done and when it should get done. And I kind of plan it out throughout the week. And then I'm able to determine how much time I need to get that done that particular day. And then after that, you still need to, you're a human being, you need to play, you need to have fun. So then, usually you just try and structure your day. However, sometimes, research is very unpredictable. So for example, today I had to stay in lab till about 8:30 fixing something because it wasn't working. And I needed to get an experiment done. So naturally, things aren't always going to go according to plan. But usually they do. So just structure your day and make sure you have goals for the day and you work towards completing them throughout the day. And you have a set amount of time to complete those goals. And then on the other end, research and academic environments can be so consuming at times that you do end up staying in the lab until like 8 or 9 at night, or even 10 or 12 at night. So then that's when I kind of initiated this new rule, because I was spending so much time in the lab that I was going to set a day that no matter what, even if I had a project, even if I had an exam, I was just going to take that time for myself and just have fun. So then my friends and I in undergrad established football Fridays, essentially, where every Friday after 5 or 6, whenever we were free, we would just go to the field and play soccer for as long as we could. And that was our let off. So different people have different ways of structuring their day or structuring their time, but just making sure that you have goals in mind and you structure them and set them and plan them throughout the week. I think that's a good way to go about it.
I think that's a very solid answer. Mm-hmm. One thing, so people understand, can you talk about, do you have a schedule when you're a graduate student? How flexible are you with that? Like all of a sudden, let's say you have to take off or something. How flexible is it? Is it like an undergraduate where you have classes to take and homework and things like that? Can you explain a little bit about that?
Sure. So I would say there's a kind of a two. So you know how people say like the 9 to 5? Well, there's 2 types of structures to the day in grad school. There's the first 2 years of grad school, or first 2 or 3 years, depending how many courses you have to take, and then the last 2 to 3 years, or 4 years, depending. So the first 2 years, I'm just going to go with the first 2 years and the last 3 years.
Okay.
The first 2 years, usually you're taking courses and doing research and applying for a bunch of fellowships at the same time. So usually your day is very busy, very taken up. So classes add structure to your day, but then you have to plan around your courses to try and get some work done in the lab.
Okay.
And I would say that that's what you try and do. That's what you should try and strive for. Or you could take that time to get homework done and then maybe work a little bit at like late afternoon to like early evening. You will have to consider it's not terrible, right? Like you will be taking classes, maybe 2 to 3 classes, but the departments usually understand that you're a grad student and that you have
Correct.
research to do. So they're not going to overload you, usually. So that's the first few years, is you have classes and then you structure your research and other responsibilities around them. The last 3 years, you're done with classes, you're a PhD candidate, and now your time is yours. You structure your time however you want it to be. If you want to, although there's a caveat, you have to make sure your advisor's okay with it. Different advisors run their labs different ways. So, for example, some advisors like their students to be there 9 to 5. Some students, some advisors like the 9 to 5 schedule. Other advisors want students to kind of fit into their own schedule. And there are some advisors that don't care. They don't care when you come in as long as you get your work done.
Correct.
So that's where I'm in. My advisor, he doesn't really mind if I come in at like 2 in the morning or like
Just get your work done.
yeah, or at 9 a.m. in the morning. Yeah, he's just get the work done and work as efficiently as you think. Work as best you think you can.
Okay.
So that's essentially what I do, is I structure my days. So even though I don't have a set schedule, I'll wake up in the morning, come to lab, get stuff ready, drink my coffee if I have to, and then start prepping stuff, and then run experiments in the afternoon, and then just take care of any extracurriculars, like maybe late afternoon, early evening.
So I kind of actually want to tie in the first topic and this topic we're talking about, your advisor and then your work-life schedule. How transparent are you with your advisor in communication and in filling him in with maybe life situations you're going through and that might be affecting your school? How can you tie both of those in?
Definitely. So you should have a very open and honest dialogue with your advisor, because many times the professors haven't done research in the lab for anywhere between 2 to 3 to like even 20 years, depending on how old they are. So they haven't actually done experiments in a while. Most of what a professor does is either teach and write a bunch of grants trying to fund the students, trying to push the science further. So again, you, however, have to be productive. You have goals that you have to achieve, and life happens. So you have to make sure that you can account for that. One of the ways that you can account for that is maintaining some transparency with your advisor, knowing what happens. So like if you have a family emergency, you tell him right off the bat. So like that's something I did with my advisor. Like, hey, if something happens in my family and I have to go back to Florida to look after my family, is that okay with you? And he said, yeah, that's perfectly fine, and I completely understand. So that was something I brought up in the very beginning when I started to get to know my advisor and work with him. Like that was something I wanted to make sure that was an option.
Okay.
And then again, if like I have events for SHIP grad that I have to do and it's going to take all day, I let him know that, yeah, this is going to take up most of my day, and you may not see me during the day, but that doesn't mean I'm not going to work or get things done. So just making sure that he knows, he doesn't have to know everything either. He just has to know what could affect your productivity.
Correct.
Yeah.
So basically, have an adult conversation, clear communication, and
exactly.
And it varies by advisor, but
definitely
we hope for the best.
Yeah. Yeah, I mean, sometimes you have kids, like my friend, my mentor here, actually, when I first started, he was a 5th year in the lab, and I just started my graduate study, and he had kids, so he had to take off like maybe 2 weeks to kind of help look after them in those beginning weeks once they were born. So like, of course, it's just life happens. Just make sure that your advisor knows what's going on and that you may need to take some time off.
Correct.
Yeah.
Because actually that's something that really late in the game, when I was going to graduate, I actually understood and learned that, yeah, it doesn't mean you're going to be a graduate student that you can't have a life outside. I was very exposed to just research and labs, but yeah, I've seen many people get married, have kids, have a other life.
Yep.
And your graduate, I guess, research and the academia there, it just becomes work. Am I kind of right? Am I kind of...
So that is the extreme of what can happen. However, it shouldn't be like that at all.
Okay.
You shouldn't be working, 18 hours a day or something, because that's just not a healthy way to live. And you're not going to be productive for those 18 hours either. You have to find out what hours you're productive what hours during the day you're productive, and then you work during those hours to get things done. Again, you're here to get a PhD. First priority is school, but you also have to let off steam because you're human.
Correct.
Yeah.
Correct. Awesome. So I guess we'll transition now into your research.
Okay.
Hopefully you'll make me understand some of this complicated math and chemical terminology. So like I mentioned, you've published a paper. I actually have one right now. I guess what are you working on nowadays?
Nowadays, I'm working on a variation of that compound.
Okay.
So that compound specifically is
Compound
iron.
I could not pronounce or say.
Yeah. Well, it's pretty simple. So Fe is iron, Bi is bismuth, and Se is selenium. So we call it iron bismuth selenide.
Okay.
Yep. And it's just like that. So then, should I go into my research now?
Yep. Go for it.
Okay. So
Floor is
basically,
yours.
this is a compound which we designed. So I work within a specific field called Spintronics. It's a short for spin electronics. Scientists and engineers, we
Okay.
like to shorten everything.
Yes.
Yeah. And that's actually, a little video of my research right there. And basically, they're interviewing me and asking me questions about the research, and I'm just going in and showing them, right here, a day in the life of the research. And here they're interviewing my advisor, Dr. Pierre Poudot, on why there's an advantage over magnetic semiconductors versus regular semiconductors. So the interview continues, but basically, the beauty about magnetic semiconductors is that they would usher in a whole new microelectronics era, such that we could achieve less power hungry, more efficient, and significantly smaller devices.
Well,
And
beyond
then,
silicon.
sorry?
This is beyond silicon, getting
Yes.
smaller than that?
Yes, exactly. Well, the issue is silicon, right? We're following the Moore's law, essentially.
Correct.
After every certain number of months, the number of transistors on a chip, which is essentially, you can kind of think of like neurons of the brain, the number of transistors on a chip doubles every so couple months. And there's this miniaturization, basically, this drive for miniaturization to make things smaller and more efficient.
Correct.
However, you can only get so small because when you get really, really small, the electrons in the silicon start to behave very erratically, right? Now you've approached the quantum limit, and things aren't as predictable as they used to be. So what has to be done is we have to find either a way to rein the electrons back in, or we can take a whole new, we can go in a whole nother direction and just make new materials that exploit a different property of the electron, which is spin.
Huh.
So electrons have charge and they have a spin. Normally, however, in silicon, for example, a non-magnetic semiconductor, the spin isn't appreciable, right? If you think of a spinning top,
Okay.
that's kind of what an electron is. It's spinning in place, kind of. It's an analogy, and it's
Correct.
it's just an analogy, but it's not. Anyway, it's an analogy, so it spins. It spins in place, and it has a certain spin, and it could be either spin up or spin down. However, in regular semiconductors, this spin is thermalized essentially, such that there's no net moment. However, with a magnetic semiconductor, this spin is appreciable. It's present because you have a ferromagnetic phase, keeping the spin of the electron in check, so to speak. And what we're trying to do is basically study the fundamental physics of why magnetic semiconductors are magnetic semiconductors and how we can make them better. So what we're doing is we're trying to draw similarities between the material properties and the Curie temperature. And the Curie temperature is essentially a critical transition temperature for the magnetic phase. There is permanent magnetism ferromagnetism, and below the TC, which is what we want, and then so like a permanent magnet, for example, is like something on your fridge, right?
Okay.
Something that kind of just sticks very easily. And then a paramagnet, induced magnet, this magnetic phase above the Curie temperature, is induced magnetism. So if you were to turn off an external magnetic field, the material no longer has a no longer has magnetization present. Yeah. Excuse me. And basically, in these class of materials, you want the Curie temperature to be as high as possible. You want it to be above room temperature, which is 300 Kelvin. The reason why is if this Curie temperature is below room temperature, right, the material is going to be in the induced magnetic phase. And then you basically have to run a huge cooling system to bring the temperature of the material back down below the Curie temperature of the material so that you can use the permanent magnetic phase of it. So you can think of the Curie temperature as like a melting temperature, for example. You know how different materials have different melting temperatures?
Correct.
Like, ice has a certain melting temperature. What's another one? Mercury has a certain melting temperature, which is significantly lower than room temperature, which is why it's a liquid when we hold it and when we touch it in our ambient in ambient conditions. Right. So the idea is to lower this Curie temperature, to increase the Curie temperature as high as possible so that we can make them useful. That's the thing. That's one of the things that's been plaguing our field for so long, is the Curie temperature in all the magnetic semiconductors that we design have been so low, but they haven't been practical. But they've still been useful because we can study the fundamental physics of them. But basically what we've done is try and make magnetic semiconductors differently so that we can achieve these high Curie temperatures. And that's what we've done. We've made one of the world's first N-type high TC ferromagnetic semiconductors.
Okay, and then how is this done? How do you get this high Curie temperature?
Chemistry.
Okay. That's where you come in.
Yes, that's where we come in. Chemistry and physics. So one of the things we have to understand is magnetic coupling. So what that means is basically how the magnetic ions talk to each other, right? So if we have two magnetic ions, right, and they're going to have a certain spin, they're going to have a certain magnetization direction, and then the electrons basically travel between them as a messenger. So if this guy isn't really all that polarized, and then this guy is, right, an electron can travel from this guy to this guy and begin to polarize this guy. So in that way, they're coupled through electrons. And electrons are carriers in the crystal. Thereby, you're getting carrier-mediated ferromagnetism. Right?
Okay, so you're going to have to say that one more time. So, okay, yes, so say that one more time. Where we come in is trying to understand the magnetic coupling in these class of materials. So then what we have to understand is the role of the electron in the crystal, right? Because this is a crystal. This is it has specific sites where atoms reside within it, and they repeat periodically ad infinitum up until a certain surface, which could be a grain boundary or the actual surface of the material. And what we're trying to understand and basically tune is the way the magnetic phase talks to each other. And in doing so, we can kind of achieve this high Curie temperature because we're able to establish a fundamental understanding of the magnetism, of the magnetic coupling, how the electrons couple any two ions, right? Correct.
Mm-hmm.
So at what stage is this? So you've created one of the first. Sorry, I'm blanking out. First in the field, but what's next after this?
What's next is to do significantly more studies to try and understand it even further. So we can do this by doing a bunch of different experiments. We can either do X-ray magnetic circular dichroism.
Okay, so can you explain what that is?
So basically, it's just blasting your material with polarized light, because normal light doesn't interact with the magnetic properties of the material very well. However, polarized light does. Polarized light can induce certain magnetic transitions
Correct.
within the electronic structure. So in this way, we can go about understanding how the electronic properties, basically how the electrons affect the magnetized states of the magnetic ions, and also vice versa, how the magnetic ions kind of affect the electron spin state as well.
So you mentioned there's more research to kind of evaluate the properties.
Definitely.
What's another type? What are you hoping to do? What's your next step?
My next step is to do those studies, so like X-ray magnetic circular dichroism, and also neutron diffraction. Neutron diffraction, to also understand the magnetic structure of the material. What neutron diffraction is basically, instead of light, it shoots neutrons at your material at specific angles, and then at specific angles it's going to diffract, which is kind of a reflection, but it's diffraction. It's not actually a reflection. So reflections occur at every angle, right? However, diffractions, because of the periodic structure of the crystal, can only occur at certain angles.
Okay.
So then you're finding those angles at which it's going to reflect the neutrons, and essentially from that you're able to determine the crystal structure by refining the data, and the magnetic structure, because the neutrons are going to interact with the magnetic spins of the ions. And then you're able to tell, like in physical space, how the magnetic ions are polarized.
So then how can we, so let's say we've studied these, we know the properties.
Mm-hmm.
How can we implement these into our technology that we use today? What's the application?
We can either use the material as is and start making devices, Magneto-Resistive Devices.
Okay, so say that one more time, because I love that name. That sounds cool, right?
Yeah, it's awesome. Magneto-Resistive Devices.
Okay.
So like the X-Men
exactly.
villain Magneto, but then resistive, yeah. Magneto-resistive. And basically what that's saying is that there's a connection between the magnetic properties and the electronic properties. Resistance is an electronic property. Resistance is basically, you have conductivity and resistance. Mm-hmm. Conductivity is how conductive your material is, right? Correct. So like metal is more conductive than wood. Resistance is the inverse. It's how not conductive your material is, how resistive it is to electrons or holes flowing through the crystal or through the structure.
Correct.
So metal is more conductive than wood,
correct.
Ergo wood is more resistive than metal.
So why do we care about a resistive material? Don't we want a more of a conductive material?
We do, but there's a caveat. You want to be able to control the conductivity so that you can make these devices. Okay. It's basically the conductivity, control over the conductivity, that allows you to establish the logic of a computer, right?
Correct.
So, for example, we can have a transistor. I'm going to go back to the example of a transistor. Okay. Remember when I said about the Morse path? Things keep getting smaller and smaller. Well, a transistor is essentially three things. You have a sink, a material in the middle, basically insulator, and then you have a source. So a source, insulator, and a sink. And basically, you want an electron to go from the source to the sink. If you have no current, no electrons flowing, that's essentially a 0.
Correct.
If you have electrons flowing, that's a 1. And that's basically how we form binary code and start doing all of these calculations within a computer. It's using a bunch of zeros and ones. Right. However, when you begin to reduce the distance between the source and the sink in these transistors, the material in the middle, the insulator, is no longer able to inhibit the electron flow.
Oh,
so
okay.
every now and again, electrons will flow when you don't want them to.
Correct.
Right? And this is problematic because it would destroy the logic of a computer.
Yeah, you have seepage, right?
Yeah, exactly. Yeah, you want a couple zeros, but you end up getting all ones.
You don't want that.
Which is, disastrous. So that's one of the issues that we're having, is as we get smaller, we approach the quantum limit, and now electrons are able to kind of tunnel through.
Okay.
Well, what that means is they're kind of able to exist in between and then kind of go through.
So that's why you want more of a resistivity property there
Exactly. So that
to
now,
prevent the electrons from flowing through from your sink to your source.
exactly, we're
Okay.
able to control the resistance now, not using an insulative material, but using not only an insulative material, but also the spin of the electron.
Okay.
So in this case, the source and the sink could be magnetized similarly, right? In the same direction.
Okay.
So then you could have electrons flowing from the source, spin up, to the sink, spin up. And there is no spin scattering because they're both magnetized in the same direction. However, if you magnetize, for example, a source spin up and a sink spin down, then there's going to be no electrons flowing because the electrons have to completely rearrange their spin. And this is what's called spin scattering. When two things are magnetized in different directions, electrons can't flow through, or at least they have a very hard time flowing through because they have to change their spin state. So now we're using the spin state to modulate the current.
So that becomes your transistor with
Exactly.
Spintronics.
Exactly. Now you can put them atomically close together even, just magnetize them in different directions,
Correct.
and there we go. Yeah.
So how much compared to the smallest transistor and the Spintronics, how much smaller can we get?
So we're still working on getting smaller. We
Okay.
haven't actually gotten any smaller than traditional, just pure semiconductor technology. But we can get smaller. We're working towards
So that's the theory, and you guys are testing and trying to
Exactly.
find all these properties and things like that.
And then we could also go another route. We can make very, very robust MRAM devices,
Okay.
right? So you have
explain what MRAM is.
magnetic random access memory.
Okay.
Well, now you have magneto-resistive random access memory. And the thing about magneto-resistive random access memory is, as you know, RAM is short-term memory, right?
Correct.
So once the power's cut off, everything you have in the RAM is completely gone. Well, the thing about MRAM is because now you're using magnetized states, when you magnetize and store information in magnetic RAM, once you turn off the power, it stays there because the material is going to maintain that magnetization. So it doesn't need power to store that data. It can exist without any external power. And this is the idea, is you can now make, right?
Yeah.
You can make non-volatile RAM. Which is
really
very
fast memory that holds
Which is
its
awesome.
state.
Exactly. And it's all going to be solid state, so you're not going to have any mechanical, like, disk spinning and having to store things on the physical disk. No.
Correct.
You're
So
just
how
gonna
is this different from a solid state kind of drive? It's you're still holding charges. I know in current there's some seepage, but you have error correction and things like that.
Mhm.
So how does RAM come in with Spintronics?
So Spintronics is basically being able to control electronic properties
Correct.
using magnetism. And that's the thing. Solid-state devices still use electricity, but I'm not quite sure how they store information, actually. Solid-state drives? I'm not sure. I have to look
Correct.
into it.
Okay.
That's a very good question. But the idea is, yes, you can make devices which are up to 80% more efficient than current technology.
Correct.
Right.
And then what's the power usage on using this technique, Spintronics?
Like a wattage, like a number?
Yeah, or I guess relative to current transistors, is it less? How do you get the spin going?
Sorry?
So from my understanding,
Mhm.
in Spintronics you could you have something spinning that way, and then in another direction you spin. But how do you get that chemical reaction going, or that reaction going? Do you apply any current? What's the properties that need to be applied there?
Oh, okay. Well, now you'd have a gate, right?
Okay.
Basically, a tiny little plate that can either make an electric field so that the electron can flow, and then maybe another plate creating a magnetic field to change the magnetized states of the source or the sink or the electrons themselves. And the cool thing is that once it maintains magnetized, you don't need power to maintain that state, and that's where it comes in.
Oh,
You have
okay.
less
That's
power. Yeah.
okay.
Mhm.
Okay. Awesome.
You have less things on at the same time.
Yes.
Yeah.
Huh. So before we wrap this up, where can people find maybe more of your research, I guess I mentioned those those three papers. Um, I guess we have this YouTube video they can see. But is there a
Mhm.
place online they can kind of follow up with your research you're doing and the latest and greatest?
Yeah, so we don't have a group website yet. However, my professor, my advisor, Dr. Pierre Prudhoe, he has a professor profile on the University of Michigan Material Science and Engineering page. He's a faculty mentor. So then you can look him up and then basically track what he's doing on that website. Or you could also follow the link to Google Scholar to see what's being done in our group.
Okay.
Mhm.
Yeah, just in case there's any maybe undergraduate students or even graduate students that are interested in your
Yeah.
research, right? Maybe they want to go to University of Michigan. Who knows?
Yeah, great place.
Awesome.
Yeah.
Well, anything else before we conclude this show on Tonight in STEM?
Can I talk about the Holy Grail of Spintronics?
Oh, I like that. Yes, you have
Yeah.
my permission.
Thank you. So, right, we can basically make new devices which are going to be better. However, there's a cool new thing about the spin of the electron that I haven't mentioned on, or that I haven't mentioned on. That's weird. That we can use. And well, I did mention it. It's the spin of the electron, but we can use it in a very different way.
Okay.
So the holy grail of spintronics would be quantum computing,
Ah.
right? So a whole lot of people don't know, but there are actually, within my field or within the academic field, there are these huge warehouses, just wall to wall, floor to roof, just huge spaces which contain a bunch of CPUs and GPUs,
Okay.
computer processing and graphics processing units. And their sole purpose is just to crunch numbers.
Correct.
And I'm telling you, huge numbers. So the amount of power that goes into maintaining and running these places is astronomical. And they're maintained by various government and private agencies.
Correct.
And that is their sole purpose. They crunch numbers. However, there is an alternative, which is called quantum computing. So regular computing uses bits, basically states, which can either be on or off. So basically, 1 or a 0, right? And a bit cannot be either a 1, or it can't be anywhere in between. It can only be a 1 or a 0, and they're mutually exclusive. If it's a 0, it can't be a 1. If it's a 1, it can't be a 0.
Correct.
And the structure of the bit has basically led to sequential algorithms. So the way it thinks is very similar to the way we think. We think through things one thing at a time. So for example, say we're trying to remember a password. We try changing one letter in that password at a time. And that's basically what a computer does. It tries an astronomical number of combinations, of different combinations, of basically permutations of the same password, of the same code, until it gets it right.
Correct. So to crack a code, to
crack
crack
a code,
encryption.
Yeah, exactly. However, let's take another analogy. So then, the way a computer would solve, say, a maze, let's say a maze, is it would try every single pathway through the maze, one at a time, until it eventually finds the proper one, until it gets through to the other side. Where quantum computing comes in is basically it allows you to try every single pathway at the same time, right? The way it does this is by using the qubit. A qubit is short, again, for quantum bit. Scientists like to shorten things.
Shorten things. That's why we get paid the big bucks, right?
Yep. And what a quantum bit is, it's essentially a very different state. So it's no longer just on or off. It could be both, or it could be anywhere in between. And this idea is very quantum mechanical. It's basically a superposition. It could be in many places and in multiple places at the same time. This is a property inherent to quantum mechanics and isn't really seen in our day-to-day. So it's really hard to understand, but essentially what I'm saying is an electron can be inside the room and outside the room or anywhere in between, whereas we can't. That's essentially what a qubit is. So it could be a 1 or a 0, or like half of 1, half of 0, or anywhere in between.
Yes.
Or even both. It could be a 1 and a 0. What this allows you to do is it allows you to create a whole new structure of thinking, basically quantum computing, or quantum algorithms, such that when you try and solve a problem, say a maze, it's not only trying each one individually, it's trying every single one at the same time. So instead of trying to instead of trying every single one at a time, it's trying all of them at the same time. Thereby, you get to the answer faster.
Way faster.
Way faster. And just to give you an idea of how much faster, say the traveling salesman problem.
Correct.
The traveling salesman problem is a very classical problem which has plagued our community
Yes,
for quite a while. And there's a number of different ways, but the way I heard it is that basically there's this company or this man who's trying to get medicine to a certain number of cities as quickly as possible because they need the medicine as quickly as possible. So he tries to chart out his route as quickly as he can, but he finds that there's so many combinations that it's nearly impossible to find the fastest route because there's just far too many calculations to be done by the human hand and the human brain. So then computers are brought in to try and solve the problem, but they themselves also couldn't solve it because just the number of combinations were so astronomical. A computer would have to be running for thousands of years just to solve it, maybe even millions or billions of years just to solve it. However, a quantum computer, because it tries every single route at the same time, it's able to calculate each route at the same time because it's able to be in that route and then in another route at the same time, right? The quantum property.
Correct.
It allows you to solve it significantly faster. So instead of trying each individual pathway, you're trying all of them. So then this reduces it from like thousands, millions, and billions of years to like 3 seconds. And that's the power of quantum computing.
It's dramatic. It's scary fast. That's how fast it is. So how does Spintronics come into play?
So Spintronics comes into play because the spin of the electron is maintained. And the spin of the electron is the qubit. Because it's quantum in nature, you can use it as a qubit and entangle multiple electrons together and do calculations that way. And it's beautiful.
Wow.
Yeah.
Wow.
However, we need materials to be able to do this, right? We don't want to run huge cooling systems to make the material usable.
Exactly. Unless you're the NSA or something like that has tons of money, right?
DoD, yeah. That's essentially one of the main problems that's plagued us is having a material that's stable magnetically at room temperature or above. Correct. And that's where we come in. Is we're trying to design and make these materials a reality so that we can meet this need.
Wow.
Yeah.
Well, that's just fascinating. You've taught me another things. Hey, you're supposed to learn something every day, and you've definitely taught me today. And definitely in the future, I want to see quantum computing made by Juan Lopez and Spintronics. Imagine that.
Material side. I'm on
the material side. Hey.
There's a ton of electrical engineering and computer engineering that has to be done to make this a reality, and I can't do that because that's just not my expertise.
Correct. But being part of that group that says,
being part of it.
I made quantum computing a reality. That's something to say.
Yeah, humbling. Yeah.
Juan Lopez on the holy grail of how Spintronics can come into play and help quantum computing. So Juan Lopez, again, thank you for your time.
No, thank you.
For your knowledge, especially that, and sharing with us your research, a little bit about demystifying graduate school. And again, if people want to kind of research and learn more about what you're doing and the research, definitely go to the University of Michigan page and look around. And then, anything else before we wrap up?
No, thank you so much for this opportunity. I really appreciate it. And let me know how else I can help.
Yeah. Nope. Thank you for your time. And definitely, I guess if people have questions specifically for you, they can email me tonightInSTEM@gmail.com.
Okay.
And then I can forward them to you with your permission so we don't
Yeah, of
release
course.
any of your private information.
Well, you
But,
could share my email if you'd like.
Okay.
JSLopez@umich, and I will try and answer as much as I can.
Yes. So again, what's your email?
JSLopez, JSLOPEZ, at U, like university, Mich, as in Michigan, .edu.
Awesome. There you go, guys.
Mhm.
So again, thank you for your time, and I guess we'll wrap up this show in Tonight in STEM. So again, like us on Facebook, Instagram. We have a Twitter page, and definitely share it with your friends. Maybe they're interested in pursuing a PhD. Juan Lopez might inspire them. So again, thank you for listening to Tonight in STEM. All right.